Hello everyone, I'm Ashish, a PhD student from National University of Singapore. In this presentation, I'm going to talk about our work on attacking Byzantine robustness in high dimensions. My collaborators on this work are Sarthak and my advisor Pratik. Byzantine robust aggregation is a classical problem with numerous applications. Consider the problem of computing an average of n data points. The data points can be thought of as d-dimensional real valued vectors. Now, let's say there's an adversary which can corrupt epsilon fraction of these data points or vectors arbitrarily to create a corrupted set of points represented by y. This corrupts the mean and creates a bias in the computation, which can be measured using the L2 distance between the corrupted mean and the benign mean. The bias can be arbitrarily large depending on how the adversary corrupts these vectors. So in Byzantine robust aggregation problem, we are interested in designing robust aggregation functions that operate on the corrupted data to compute an estimate of the mean while reducing the bias. One of the very important applications of Byzantine robust aggregation is to perform robust machine learning. For example, it is crucial for the robustness of stochastic gradient descent algorithm in ML. In SGD, the gradients are computed in every training round over training data, and the average is used to update the model. Now, there have been several attacks and defenses that have been proposed for stochastic gradient descent. For example, poisoning attacks, which also involves backdoor attacks. And at the crux of all of these attacks and defenses, um, the the you can think of them as they're corrupting this average gradient to poison the trained model to exhibit arbitrary behaviors that the attacker wants. So our findings apply to any such application which involves Byzantine robust aggregation. However, for concreteness, we'll focus on evaluating them against untargeted model poisoning attacks. This attack is typically performed in distributed stochastic gradient descent setting where training is performed over locally on multiple devices and the gradients are aggregated at a master device. So let's take an adversary here, which controls an epsilon fraction of these devices, which means that this adversary can completely poison the gradients, send arbitrary gradients basically to the central server for aggregation. The goal of untargeted model poisoning attacks is to bias the average gradient to reduce the training accuracy of the trained model. So in such scenarios, Byzantine robust aggregators can be vital to limit the bias and reduce the effect of model poisoning attacks. In machine learning, especially in the current day, the dimensions, the model sizes is huge. For example, for LLMs specifically, they can range in trillions, and even for typical computer vision tasks, they can be in several millions. So in such high dimension, the the main challenge of robust aggregation is to balance between the computation complexity of these robust aggregators and the bias that they can provide. So we know of many classical algorithms which which do robust aggregation very fast. So for example, coordinate-wise mean and median, they are fast in the sense that their time complexity is linear in NND. But the problem with these aggregators is that their bias increases with square root of dimensions. So in high dimensions, they are far from being optimal. The first breakthrough happened in 1960 when Tukey median was proposed. Tukey median achieves dimension independent bias. Actually, it achieves statistically optimal bias. But the problem with Tukey median is that its time complexity is exponential in the number of dimensions. So for a long time, nothing happened until very recently, filtering-based aggregators have been proposed. So they are strong aggregators which achieve dimension-independent bias, just like Tukey median. And at the same time, they are the first aggregators which have time complexity polynomial in NND. So even now, it's very common for us to see coordinate-wise mean and median kind of differences for higher dimensional machine learning settings, because essentially D is very large. So even though filtering-based differences have time complexity polynomial in D, the D cube turns out to be very high for implementing anything in practice. So so the implementations of filtering based differences as is, like if you implement them as is, they can take a long time just because N and D can be very high. But even then, only last year, the first implementations for these, the practical implementations for these have been proposed. So even though in theory the time complexity is order n d cube, these implementations seem to be much faster than that in practice. So in this work, we address two important research questions. First one is that can we design strong, robust aggregators which have time complexity linear in NND? Why do we want to address this? We want to address this because it seems like as we go forward, as dimensions increases, the model size increases, this seems to be very desirable. Uh, the second question is, well, some implementations recently have already shown that you can have efficient filtering-based aggregators uh, for high dimensional machine learning settings. So our question is, do these state-of-the-art robust aggregators, do they really provide dimension independent bias? Addressing our research question one, our first contribution is that we uncover a new fundamental computational vulnerability in designing and implementing any deterministic robust aggregator with statistically optimal bias guarantees. The vulnerability is as follows. We prove that any deterministic robust aggregator, strong robust aggregator, that is designed to provide a dimension independent bias implies finding the direction of maximum variance of n d-dimensional vectors in the worst case. What that means is we design hard instances where this thing happens. To the best of our knowledge, the best known algorithms that we know of to compute almost exact maximum variance direction has the following time complexity. Therefore, we believe that designing a strong, robust aggregator with linear time complexity in an ND is not possible unless there's an advance in the problem of finding the direction of maximum variance. Now, addressing our second research question, which is, do the practical implementations really provide dimension independent bias? We find that they do not. To prove that they do not, we design a new attack called Hydra against filtering-based robust aggregators. Hydra provably generates optimal bias, uh, and thus showing that the analysis of these robust filtering-based robust aggregators is tight. So it matches their upper bounds. And against their implementations, Hydra generates bias proportional to root D. As in, it shows that the implementations which seem to run very fast have do not have dimension independent bias as expected, as you would expect in theory. Consequently, we also show that Hydra can result in over 70% drop in training accuracy against these defenses, whereas prior state-of-the-art attacks do not. So this is what I mean when Hydra achieves optimal bias. Here we show the result of training a model on an image classification task with implementations of strong robust aggregators as defense and Hydra as an attack. On y-axis, you can see the bias, and on x-axis, you can see the number of dimensions. So first, we show that the bias should increase with dimensions in theory for the implementations of strong aggregators, which should have ideally provided dimension independent bias. Next, we can see that Hydra successfully matches the expected upper bound on these implementations. Ignore the fact that Hydra line is slightly higher than the upper bound. This happens because of imprecision when using the constants given in theory. To summarize, the point is that the bias of implementations of filtering-based aggregators is not dimension independent as expected. And another important thing to note here before moving forward is that Hydra is only designed to exploit the vulnerability in the implementations of filtering-based aggregators, and it's not expected to beat other defenses. Hence, Hydra is not expected to be stealthy. To position our contributions better, I want to first explain the known challenges of robust aggregation in high dimensions. First, let us understand what are the limits on bias, achievable bias, and in robust aggregation, and the role of variance. In one dimension, assume that there's a benign set of vectors with their mean at origin and variance very large or unbounded. In this case, we can always place a corrupted point in such a way that the mean shift by arbitrarily large amounts. Therefore, it's important for the variance of the benign distribution to be finite and small. Secondly, it's a known fact that robust aggregators can never achieve bias lower than order square root of epsilon times the variance, the benign variance. This can be proved, but here I'll try to give you an intuition. So basically, you can come up with two benign inputs, which have same 1 minus 2 and epsilon, and 1 minus 2 epsilon fraction of points, same, and epsilon fraction of points different, such that their means, their corresponding means, have a distance of order square root epsilon times variance in between them. And when you give the whole set of points to a robust aggregator F, F cannot distinguish between those two benign distributions. So it's statistically indistinguishable. These two are statistically indistinguishable for F. So in high dimensions, it is not so easy to compute a robust aggregator. To understand this, let's just perform coordinate-wise aggregation, which is a natural approach to extend what we know from single dimensions to high dimensions. So we compute a robust estimate of mean in every dimension, say using median, and we do it one by one. If we do that, we can see that in each dimension, we would get order root epsilon bias. From the previous slide, we know that this much is expected. Now, if we do this for every dimension, this bias just accumulates to have the total bias, which is proportional to square root of d. So clearly, coordinate-wise defenses, the naive defenses, are not optimal and not sufficient in high dimensions. So instead of finding the mean by taking projections onto each coordinate one at a time, we can take projections on all possible directions. So this is one idea. Now, if we do this, so this idea is not new. This is the idea of Tukey median, basically. The point is this achieves statistically optimal bias or order square root epsilon bias. The problem is any procedure that aims to do this in this way would have a time complexity which is exponential in d. Recently, a line of work has shown that instead of looking at all directions, it might be sufficient to consider the direction of the maximum variance. The idea here is that corrupted points are more likely to be outliers in the top variance directions. So these are the filtering-based defenses or aggregators proposed in 2016. And they show that the aggregators achieve statistically optimal bias in polynomial time in both N and D. So the key idea of filtering-based defenses or aggregators is to iteratively filter out the outliers along the maximum variance direction. So to separate the outliers from the inliers, they use a threshold which is proportional to the benign variance. And this threshold determines the number of inliers versus outliers that they would remove in every iteration. So in the first iteration, you remove some outliers, and then you recompute the maximum variance direction and remove some more outliers, and so on and so forth. So this happens iteratively until the maximum variance of the resulting set of points is less than the threshold, it falls below the threshold. So here are the computational costs for filtering-based robust aggregators. These computational costs primarily arise in filtering-based aggregators because they compute the largest eigenvector of a d by d covariance matrix for computing the maximum variance direction. So while being polynomial in time, because n and d are in millions, this is not very desirable. So addressing this question, can we design linear time strong aggregators? Our first contribution in this work is that we show that any deterministic strong aggregator will be at least as computationally expensive as computing the almost exact largest eigenvector in the worst case. We show this with reduction proof. We construct instances where if we have access to a deterministic strong aggregator, then it can be used to compute the exact largest eigenvector with the following time complexity. So to the best of our knowledge, for such instances, computing the largest eigenvector takes so much time. Now, now the state-of-the-art implementations of filtering-based aggregators, like they are designed to be much more efficient than order D cube in theory. So the way they do it is that they chunk the dimensions into like a small chunks, and then they run robust aggregators over each chunk. So you take, let's say you take a chunk of size 1000, then you take the first 1000 dimensions and you run the robust aggregator there, and then you take the second 1000 and the third 1000, and you keep doing this. So this is how they make it very fast, the filtering based differences, the aggregators. So now the question is, do they still have dimension independent bias? So other attacks which already exist, they are not optimized to beat such defenses and end up placing points too far from the mean. Hence, the corrupted points get filtered out in practice. Hence, prior attacks cannot be used to check whether these defenses really have dimension independent bias. So as our second contribution, we design an attack called Hydra to show that the implementations do not have dimension independent bias. In Hydra, our key idea is to place corruptions within the threshold of filtering based aggregators to avoid filtering. To do that, we analytically compute the position of such corruptions such that the corruptions do not increase the variance beyond the threshold given by the benign variance. And because in Hydra we want to perform untargeted attacks, we choose the direction as opposite to the estimated benign mean. We show that Hydra results or generates optimal bias for filtering-based aggregators. Once we know how to bypass filtering using Hydra, we could use the same thing per chunk for the practical implementations. So in the first chunk, we use Hydra to corrupt the points to get so much bias. And we can do the same thing for the second chunk, and this can keep going on for every chunk. So against the practical implementations in high dimensions, the total bias generated by Hydra would scale with the number of chunks. So what this means is the bias generated by Hydra is dimension dependent, or the practical implementations basically do not provide dimension independent bias. So we also evaluate Hydra in many image classification tasks to show whatever we claim in theory. So the first evaluation goal is that does Hydra create large bias when training on tasks with strong aggregators? And the second one is like how much is the performance drop because of the bias created by Hydra? So we also compare Hydra against other baseline attacks on these classification tasks, image classification tasks. And the CNNs that we use have dimensions in millions, up to millions. So the first result is that Hydra generates optimal bias, whereas other attacks fail. And the second empirical result is that Hydra generates sufficient bias to destroy model performance at 20% corruptions. The destruction is almost up to 70%. So the reduction is a lot compared to the prior attacks. So we observed this in many other classification tasks as well. Please refer to our paper for checking more results. So these are the key takeaways. We have two contributions. The first one is that we uncover a new computational vulnerability for deterministic strong robust aggregators. And then two, we show we design Hydra, an attack to exploit the vulnerability in filtering based aggregators whose existing implementations actually provide order actually provide dimension dependent bias. Thank you. You can check out Hydra here, and you can also check out our other work on our websites.